Hello, everybody, and welcome to the Wildwood Institute for STEM Research and Development, the WISRD Podcast, brought to you by the WISRD Publications. WISRD is a student-run STEM research and engineering institute run out of Wildwood School in Los Angeles, California.
Today on the podcast, we'll have a conversation with two WISRD members, Myles Kenny and Molly Stevenson, on their research in aerodynamics and engineering.
Myles and Molly, welcome to the show.
Thanks for having us.
Yeah, so you two are principal investigators in the aerodynamics lab. Tell us a little bit about your work.
So our lab is split into two sections, theoretical and experimental. I work on the experimental part in manufacturing and design of the water rocket and the static rocket engine testbed.
And I work on the theoretical side, applying math, physics, and fluid dynamics to describe how the bottom moves and how the fluid exits out the rocket.
So Myles, you mentioned fluid dynamics. Can you explain that to us a bit?
Of course. So fluid dynamics, simply put, is just a study of how fluids move. And so with our water bottle rocket, we have water and air, and they're moving out of a bottle rocket. Seems simple, right? Actually, it's not simple at all. And so what I'm trying to create or derive is how we use fluid dynamics to describe the impulse or the thrust of the bottle rocket. So we're using Bernoulli's principle, which studies the conservation of kinetic energy of the whole system. And then we're also using ideal gas law, which kind of equates pressure, volume, and temperature. And so these are really helpful things when we go to the experimental side and see what kind of sensors do we need and how do we set up the lab so that we can get data and then analyze it and then see it, match it to our theoretical equation.
So after all this research and calculation, how do you apply these concepts to your work? Like you talked about kind of translating that over into the experimental side.
So the static rocket engine testbed has been the testing system we've been using. It is a static rocket launch plate where we have our first iteration actually had a rocket launching from the bottom to a force plate at the top. We realized that something went wrong when the bottle bounced against the force plate, causing issues in our data. The second iteration, the bottle was attached to the force plate, but there was too much force from the rocket. So with our third iteration, we decided to add a second force plate, but using the idea that the sum of the forces would be the total forces applied by the rocket, but we couldn't exactly get the force plates to be in parallel, which was too difficult with the tools we have. Our fourth iteration we are currently working on, and it is a bottle with the top cut off, and we're adding a lid that will be able to test pressure inside the rocket, temperature inside the rocket, as well as force through arms.
Right. Can you give us a bit more detail about how you guys collect your data and also how you analyze and synthesize that data?
Yeah, so we use Pasco software. It's this, you kind of see it in a lot of physics departments in high schools. And we use this force sensor that can go onto our computers, and we can actually see in live time the force versus time graph. And then what I do is we take the area under the curve of that launch or that data of the force versus time graph, and that gives us our thrust. And so we use that and we compare that with the water versus air ratio, and then we should be making hopefully a bell curve to see what the optimal range is. And so that's how we implement some of these Pasco systems. Currently, we are working on a new design that Molly mentioned briefly about how we're going to use pressure probes and temperature probes to see how the pressure and temperature are changing with respect to time. And then using my theory, we should have a very similar curve with respect to the force versus time graph, and then my theory
You mentioned temperature.
Mm-hmm.
Are you working with rocket propulsion, or I thought we heard you were working with bottle rockets?
Right, so it is a bottle rocket and it's staying stationary, so it's kind of different. We're not launching it up and seeing the altitude. And so because it's staying stationary, there's several things that are in our favor. For instance, it's easier to control, like to measure the temperature. When you have probes flying out in the air, it would be kind of hard to actually measure what's going on. So the temperature part of it, going to kind of backtrack. So the theory starts from this rock equation, the classic rocket problem, which kind of shows how the momentum is conserved through a water bottle rocket, or in this case, it was just a rocket in space. And the temperature part comes in, like I said, with the ideal gas law, which kind of shows how a volume of air is changing with respect to pressure and temperature. Now, the volume of air times density will give you a mass, and that mass of air you can equate to the mass of water, and all of a sudden that becomes a integral part of mapping out the change in momentum, the mass and velocity of the rocket. So that's kind of a little nitty gritty of the theory side. I think especially with the theory side, and being high school students, rocket science is challenging, and we've definitely experienced that. We started this lab in 9th grade, and some of these things were way over our heads, but every year we've just gained more and more knowledge, and more knowledge in math and physics, and so all these intricate parts and variables going on have become more and more not common knowledge, but a little more interconnected, and we've been able to actually describe these systems.
Do you guys manually solve your problems, or do you use like a software to help you do your equations?
Do you mean the math part? Or?
Yeah, like when you're working with the rocket equation or other things, do you use a software, or do you actually solve it out by hand, old-fashioned style?
No, we have to solve it by hand. I work currently with Scott Johnson, who's a fellow scholar for WISRD, a visiting scholar, and he's also my physics teacher, which helps. And so he's helping me with some of these mathematical equations. So.
Cool. So it sounds like you guys have a lot of insight into how all these variables affect your process and your trials with the water bottle rockets. And you also mentioned that your work with the rockets has evolved and required a lot of iterations and I guess like failures before you arrived at this point in your process. So can you kind of speak to how that's influenced your work, especially in WISRD, where we work with a context-based learning model?
So learning from failure is just such an important part to the Institute model, and something that we've both experienced with all of these iterations of the static rocket engine testbed. We've had to look at every launch and see what went wrong and how to fix it and how to find patterns in our data, and every single iteration has come from looking at the overall launch and finding the specific parts that don't work to create a better launching platform.
If anything can go wrong, it will go wrong, and we can definitely say that has happened. And I think this just shows something that's really valuable to the Institute model that you don't really get in a traditional science classes. This is real science. Science is challenging and hard, and it's a lot of failures. Typically speaking, when you go to a science class, the teacher will give you some type of project or lab that is meant to succeed, right? You're either putting some chemical and some reaction, and you expect something to happen. For Molly and I, we didn't have any guidelines or procedures to follow. We had to create them. And so we really had to play around with it. And a lot of times science is just trial and error. And so I think that's just been really valuable for me, and something I'm going to definitely take forward moving on to college and beyond.
So it sounds like your work in research in aerodynamics has had a significant effect on your understanding of physics and mathematics and engineering.
Mm-hmm.
Can you go into a bit more detail?
Yeah, so I think that we've had to learn the physics of how projectiles and rockets and motion and even fluid dynamics as well as aerodynamics, and all of that has played its role into how we design the static rocket engine test bed, or what equations we bring into our theory to decide what gets used, what we don't need to consider, to decide what we don't need to think about, but what's really important.
Yeah, for me especially, coming into my calc classes or my physics classes, I feel like this lab has really given me a step up to maybe some of my other peers, because I see like a differential equation, or I see momentum. I'm like, oh, this is not a piece of cake, but like at least I'm comfortable with it because I've had experience and exposure in WISRD, and so especially Molly and I both do Calc 2 right now, and there's a lot of things that we learn in Calc 2. It's like, oh, this makes sense. Like this is what's actually going on in our lab, and then sometimes math is very theoretical, and I actually like theory, so that helps. But seeing it actually in physical form and in the real world is super valuable, and I think WISRD has given us that opportunity to see some of these more theoretical subjects in a practical world.
Yeah, so given your experiences, what do you guys think that the education community has to learn from work like yours in terms of teaching STEM-related topics?
I think that it's the STEM world has to learn in education is having a application to a lot of the theories we've learned, and I think that's been such an important part to our learning, and also figuring stuff out and learning patience and how to reflect on work.
Yeah, I think one of our goals towards the end of this year is to create some type of educational tool from our lab, and to encourage other schools and other institutes to try this approach of trial and error. It's nothing new, but I think something that WISRD does really well is this contextual learning, and I think especially in sciences, there's so much value that you can get from just failures and accepting failures, and how do you move forward, and it's something that schools kind of struggle at. Sometimes you can just do tests and look at a textbook, and you may be good at doing tests, but when you go in the real world and you need to solve problems, you want to educate those students that are going to be the new problem solvers, and so at least what I've seen, WISRD is doing just that.
All right, and before we go, we talked a lot about context-based learning in this podcast. How would you guys define that in terms of your work and what you've been doing in WISRD?
I think context-based learning for us is a lot of figuring out different solutions and figuring it out in the moment and collaborating with others in that, but really picking a topic but learning so much outside of the topic as it applies to the topic.
Yeah, it's helped me understand more of like my community around myself. Like I feel like we've collaborated with engineers and like 3D printing, because we need to print some designs for our bottle. We've collaborated with physicists, with mathematicians, and so it really comes into you can't always do it by yourself, and you need a supporting group and community around you, and so realizing that you want to surround yourself with people that are not only interested in you but have other talents, and to be able to like find and use their talents to your advantage. It's just been really awesome.
All right, well, Myles and Molly, thank you for coming on the podcast today. And would you like to tell the audience where we can follow your work?
We have our journal, the Aerodynamics Fluid Dynamics page on WISRD.org, as well as the WISRD Twitter account.
Yeah, and thanks for having us.
Thank you
All
so
right.
much.
Thank you.